In December 2023, Matthew Scroggs put up a puzzle advent calendar on his website, and I enjoyed solving those puzzles immensely. Afterwards, I realized it might be interesting to share with you my thought process in solving these puzzles. It probably would have been better if I had saved up all the puzzles for after Christmas and did a live solve of me doing them, but here we are. If you enjoyed this video and do want to see me struggle live, tell me in the comments and I'll try to remember next December. You can find a link to Matthew Scroggs' website down in the description if you want to have a look at the puzzles yourself and at his solutions. I haven't looked at the official solutions on the website yet, I just double checked whether my answers are correct. These 24 puzzles all give you a 3-digit number as a solution, and those numbers will then be used in an overarching super puzzle which you could have solved to win a prize. So let's get started with day 1. Each interior angle of a regular triangle is 60 degrees. Each interior angle of a different regular polygon is 178 degrees. How many sides does this polygon have? Each interior angle of a polygon, there's an explicit formula for the interior angles in a polygon, and we can just use it to solve for the number of vertices. In this case it's 180. What I usually prefer when working with regular polygons, however, is to think about the exterior turning angles. If you imagine walking around the polygon, you have to turn by beta to get around the corner. These turning angles have to sum up to 360 degrees, which is basically directly the second line we have on screen. And that is more obvious for me than the interior angle formula with the -2 in the numerator. But at the end of the day, we have a formula and can use it. December 2nd. Holly adds up the first 6 even numbers, then adds on half of the next even number. Her total is 49. Here the example at the start is important because it tells us that 0 isn't considered the first even number. Next, Holly adds up the first n even numbers, then adds on half of the next even number. This time our total is 465,240. What is n? In this case it's straightforward to write down what we have. We add the numbers 2, 4, 6 and so on up to 2 times n and then n plus 1. In the first part we can factor out the 2, then we have the numbers from 1 to n summed up, for which we have a nice formula. We can massage it a little and end up with n plus 1 squared, and then we can just solve for n and we get our result. Regardless of the actual puzzle, the statement here is very nice. There are numerous similar formulas. For example, the sum of the first n odd numbers is always a square, namely n squared. The sum of the first n powers of 2 is the next power of 2 minus 1. And here we have something similar. The sum of even numbers plus half of the next even number is always a square number. Maybe not outstanding enough to actually remember, but a very nice statement nevertheless. Day 3. What is the smallest multiple of 15 whose digits add up to 15? Here I just wrote like 2 lines of code that iterate through all the multiples of 15 and we get 195. You could force it with a bit of logic, I think. Every multiple of 15 has to have a 5 or a 0 at the end. If it's a 0, the first 2 digits have to be rather large to sum up to 15. If it ends in a 5, the first 2 digits can be smaller because they only have to sum up to 10. In particular, the first digit can be a 1, so 195. But that's not really a good strategy in a general case. If you have, for example, multiples of n whose digits sum up to n, this argument wouldn't work in this form. So I don't know if this is a valid strategy to use. And the only other thing I want to say about this puzzle is that we will see the sum of digits of a number a lot in these puzzles. And I will often call it the cross sum of n instead of the sum of digits of n. It's not super uncommon, this term, but it's definitely not standard. But I'm used to it from German and so I will use it. Then on to day 4. What is the largest possible value of n for which n factorial minus 123 over n minus 123 is an integer? I wrote a little computer program that iterates through small numbers b for n factorial minus b over n minus b, and it seems to always result in n equals 2b as the solution. This also fits the given example, but it still felt more like a lucky guess than an educated one. Be that as it may, 2b being the maximal possible value is something I could then prove. If we look at any number which is potentially larger than 2b, we can write it as 2b plus k for a non-negative k. And after you plug it in, 2b plus k factorial minus b over 2b plus k minus b, the denominator becomes b plus k and we can split the fraction. b plus k is always smaller than 2b plus k, so we get the normal factorial definition for the first summand, but the factor b plus k somewhere in the middle is missing. This is definitely always an integer. And the second term, b over b plus k, is an integer if and only if k is 0. That proves what we claimed at the very first line, that n equal to 2b works out. In the actual puzzle, it's 246. Next, on day 5, we have a variant of a magic square, which will come up a couple of times. We have the important rule that the terms should be read left to right and top to bottom, ignoring the usual order of operation. So for example, 4 plus 3 times 2 is 14, not 10. We always evaluate the expressions from start to finish. Lastly, the solution for the day is the product of the numbers in the red boxes, which I will ignore. I will just be content with solving the grid for this video. Let's get rid of the lower part to look at a larger version of the grid. We see it is basically a magic square where we add up to 15 and we have to use the numbers from 1 to 9. But in the second column, there's a bit of weird stuff going on. The first thing to realize is that the first two boxes in the second column multiplied with the third one must result in 15. That means the third box in column 2 must be a factor of 15. So it's either 3 or 5. And from here on out, I just didn't have any good idea where to look next, so I just fiddled around. I tried out 5 at the bottom box first, because 5 is usually in the center of a magic square, and I thought maybe because the square here is unusual, that 5 is down there. I also tried to force most of the triples you would find in a normal magic square into this one, and then I found the solution. Maybe there's more insight to have here, maybe you have a better way to find the solution after the 3-5 entry at the bottom, but yeah, basically just trial and error for a while. On day 6, it's where it started to get very interesting. There are 5 ways to tile a 4x2 rectangle with 2x1 pieces. How many ways are there to tile a 12x2 rectangle with 2x1 pieces? If you've never seen this, it's great that there's an example because it can be a bit confusing at first. I, however, have seen this before and I immediately knew the solution, which is a bit unfortunate for the enjoyment of such a puzzle. What we get here is one of the many ways to introduce the Fibonacci sequence. If you have a teacher who doesn't want to just smack you over the head with a definition of the Fibonacci sequence, they will usually use this one or something similar. Let's get into it. We are looking at a rectangle which is 2 units high and n units wide. Then we have to tile it with these domino blocks, which are 2x1. To formalize the problem, let's define t of n as the number of such tilings of the n×2 rectangle. Then we can look at the case that the last piece on the very right of the rectangle is a vertical piece. That means we have an n-1 wide rectangle on the left to fill. And we know by definition there must be t of n-1 ways to do that. Or, in the second case, we have 2 horizontal pieces touching the very right border. That leaves us with an n-2 wide gap on the left. And we know that there are t of n-2 ways to fill it. Because these cases are mutually exclusive, they can't happen at once, the total number of tilings must be the sum of them. And this is the same recursion formula as the Fibonacci sequence. The only difference might be that it starts at a different place. So let's have a look. If we take the Fibonacci sequence itself, it looks like this. F of n is the nth Fibonacci number. It starts with 1, 1. If you look at our tilings, we see that if our rectangle is just 1 unit wide, we only have one way to fill it, with one vertical piece. And if it's 2 units wide, we can fill it in 2 different ways, with 2 vertical or 2 horizontal pieces. So our sequence starts with 1 and 2, and then we can use the recursion formula, and we will end up with a Fibonacci sequence that is shifted by 1. We can now either do the recursive formula several times, or look up the 13th Fibonacci number, and we will get the solution for this day. Day 7. How many sets, including the empty set, are there that contain numbers from 1 to 14, that don't include any consecutive integers? This was a very weird puzzle for me. I immediately saw that there is some kind of recursion probably going on, but I couldn't see what actually happens. So I started to write a computer program which iterates through all possibilities with a recursive function call. And after a few lines, I had the recursion formula for the Fibonacci sequence again on my screen. Somehow I didn't realize it without writing code. So let's make a new definition. Let S of n be the number of sets of digits 1 to n with no consecutive numbers. Then we can do something similar as in the last puzzle. we can look at the case that a set that doesn't contain the highest number n we're looking at. There are s of n minus 1 different ways how to build these types of sets, because they look the same as if the highest possible number was n minus 1. But if it does contain n, it cannot contain n minus 1. So the highest possible next number that might be in it is n minus 2. So it is s of n minus 2. Again, we get the same recursion formula as Fibonacci. We will look at the start of our sequence here too. In this case, if you use the digits up to 1, there are two ways to build such a set. That's the empty set and the set with 1. If you go up to the digit 2, there are three sets we can build. The empty set, the set with 1, and the set with 2. The set with 1 and 2 is forbidden, because then 1 and 2 would be consecutive. This means it is the Fibonacci sequence again, but now shifted by 2. We now have to look up the 16th Fibonacci number to get our result of 987. In the finite group Discord server, Matthew Scroggs asked me to solve a bonus question at this point. How can you relate the two puzzles of day 6 and 7? How can you turn a tiling of an n by 2 rectangle into a set containing non-consecutive digits, and vice versa? Remember that the sequences are shifted against each other, so it might not be straightforward. It is a nice exercise which I will give to you as a homework now. How can you relate the tilings from day 6 and those non-consecutive integer sets from day 7? Here we will continue to day 8 though. Noel writes the numbers from 1 to 17 in a row. Underneath, he writes the same list without the first and last numbers. Then continues this until he writes a row containing just one number. What is the sum of all the numbers that Noel has written? I think you can derive a general formula for this. You have to realize that if you want to end up with a single number, we have to start with an odd number. So let n be 2n plus 1. If we say that the starting line is line 0, then the highest number we have is always n minus k in line k. Moreover, the numbers from 1 to k are left out at the start of line k too. That means we can sum up all numbers from 1 to n minus k and subtract the sum of all numbers from 1 to k. We get this relatively big formula here. We can simplify it either manually or by Wolfram alpha, and we will end up with m plus 1 to the power of 3, which is again one of those really nice number theoretical identities. Summing up all numbers in this triangle pattern will always give a cube number, which is quite nice. I did, however, when I solved the puzzle, was to write the numbers all into an Excel sheet, because there are so few of them, copied the column, and I systematically deleted the excess numbers to be left with the triangle we want. And then I just let Excel sum them up. Solving the general case is still a good exercise though. On day 9, we have a very straightforward geometry puzzle. The diagram below shows a rectangle. Two of its sides have been colored blue, a red line has been drawn from two of its vertices to the midpoint of a side. The total length of the blue line is 50. I will ignore the units. The total length of the red line is also 50. What is the area of the rectangle? Let's label the sides A and B. The blue line tells us that A plus B is 50, and the red line, or one of those triangles to be precise, tells us by the Pythagorean theorem that A over 2 squared plus B squared is 25 squared. We now have two equations for two unknowns. We can solve them. A is 20, B is 30, and we get that the product, the area of the rectangle, is 600. On day 10, we had a counting problem again. How many integers are there between 100 and 1000 whose digits add up to an even number? My intuition directly told me that it probably is 450, because increasing by 1 changes the parity of the cross sum. So if you start at 100, the sum of digits is odd, and if you add 1, it is even, and if you add 1, it is odd again, and so on. We have, well, if you ignore 1000, we have 900 different numbers, so half of them should give us 450. But then I was thinking, well, if you go from 479 to 480, the cross sum stays even. But at the next 10 increment, from 489 to 490, the cross sum stays odd. Now, it could be, if you make this change to the next 10th digit or the next 100th digit, it could be that it will also alternate between staying even and staying odd. And those should compensate each other, which would leave us with 450 still. But then I felt this is exactly that kind of problem where I could make many dumb counting mistakes. And because it's just 900 numbers, I wrote a computer program to check. And it told me, yes, it's 450. There's probably a good way to write this idea down, changing the parity by going up once, and not changing it, going to the next tens digit and so on. But for me, it was easier to ask my computer than to think for myself. Day 11 gives us the next variation of this grid puzzle, and now it becomes quite interesting because we have a division involved. As with the last one, the more or less obvious entry point is the cell where we have to multiply something. If we look at the third column, for example, the first idea is that the first two cells divided by each other times the last one has to be 30. So this box must be a divisor of 30. The same argument in the row. The first two cells divided by each other times the last one must be 3. So it must be a multiple of 3. But the divisions might result in something like 1/2, 1/3, 1/4. And then we have to multiply by an appropriately larger number to compensate. If you look at the column, that's very restrictive because we can't have, for example, 1 and 2 in the first two boxes, because then the last box, the highlighted one, would have to be 60. So for the column, we only have the actual proper divisors of 30. And it can't be 1, because then the first two cells would have to have a ratio of 30. And it can't be 3, because then the first two would have to have a ratio of 10, both of which are impossible with the numbers from 1 to 9. That leaves us with 5 and 6 for the bottom right box. Then we can do the same argument for the row. It can't be 5, because then the first two boxes would have to have a ratio of 3 to 5, which is impossible. Unless we use the numbers 3 and 5, but we already used up the 5 for the last box. So it must be a 6 here, which directly gives us a 5 to 1 ratio for the two remaining column cells, which just means 5 and 1. And for the row, we now need a 1 to 2 ratio. Because 1 and 6 are already gone, the only pairs which are possible are 2 and 4 and 4 and 8. And from here on out, it was again just trial and error to find the correct solution. Maybe there's a clever way to find out which one of those two different cases is the actual correct one, but I just tried it out and fiddled around for a bit with the rest. For day 12, we have another puzzle involving factorials. What is the smallest value of n, such that 500 factorial times 499 factorial times 498 factorial all the way down to 1 factorial, divided by n factorial is a square number. Because 500 factorial is so ridiculously large, it is clear that I, at least, can't use a computer program to solve that. So we have to think a little bit about what we are having here. But I still used a little Ruby script to test out the statement for small values. So I was looking at b factorial times b minus 1 factorial all the way down to 1 factorial divided by n factorial. And let the computer check what the smallest n is for which we get a square number. And the idea seems to be that it is b over 2. Because I couldn't see it, I did a small example from 10 factorial down to 1 factorial, explicitly with all the factors. The first idea I had was to factor out the 10 of the 10 factorial, which gives us two 9 factorials, which we can put together to form a square number. But then I was stuck for quite a while and couldn't see the continuation. We can do the same trick for all other pair of numbers. Factor out the 8, which gives us 7 factorial squared, factor out the 6, which gives us 5 factorial squared, and so on. We can then collect all the squares and non-squares. If you now look at 10, 8, 6, 4, 2, that's like twice a factorial. So we can factor out several 2's, which will leave us with the sequence 5, 4, 3, 2, 1, which now is an actual factorial. So if you divide that by our computer-generated guess of n equals b over 2 factorial, or in this case n equals 5 factorial, we would have a square number as the second factor. What's left to do is argue away the exponent 5, because 2 to the power of 5 is not a square number. My computer earlier also suggested that it only works for multiples of 4, which makes sense. We formed b half many pairs, and then we factor out that many 2's. And in order for 2 to the power of b half to be a square number, b half must be even again. So the number b we started from must be a multiple of 4. And well, since 500 is a multiple of 4, it would work out. We would get 2 to the power of 250. What I still don't see as of recording this is why this 5 factorial here in the example, or the b half factorial in general, why is this the smallest number for which this works? If you have an insight into why it's obvious that this b half factorial must be the smallest number, then please let me know in the comments. Here, however, we will go into the second half of Matthew's puzzle collection, and for day 13 we have this cross number puzzle here. Across we have firstly today's solution number, and then we get clues like a multiple of 5 times the sum of the digits of 2 down. After a little pause, I thought, okay, it's probably best to give each cell a name, and then reformulate the clues in terms of those variables. For example, a multiple of 5 times the sum of the digits of 2 down would turn into the number DEF is 5 times x times b plus e plus h for some number x. Here I'm using these square brackets in the beginning to indicate that it is the number built from the digits DEF and not like the product of D, E and F. Probably not necessary, but just to be safe. And with this setup we can continue. The next clue, GHI is at least 2 times CFI. ADG is the sum of GHI and CFI. B is 9 times D plus E plus F. And CFI is larger than BEH. With that we can remove the original clues and just work with these here. The first thing I did was to tackle some low-hanging fruit. First, clue number 1 tells us that DEF is a multiple of 5, which means its last digit F must be 0 or 5. Clue number 3 tells us that G has to be an even number, because the last digit is produced by adding I and I. Next we can take the inequality from clue number 2 and plug it into the right hand side of clue 3, which gives us ADG is at least 3 times CFI. So for that to work out, CFI can't be too big and ADG can't be too small. Concretely, A must be at least 3 and C is at most 3. We can then use this equation we generated here and add in clue number 5 to get another lower bound for ADG. And it tells us that ADG is at least 3 times BEH. With the same argument as before, B is also at most 3. So we limited many digits to very few numbers already, which is quite nice. Let's put that aside and let's tackle what I think is probably the main insight of the puzzle. Clue number 4 tells us that B is a multiple of 9, and it also means that the cross sum of BEH is a multiple of 9. If we now go back to clue number 1, it tells us that if B plus E plus H is divisible by 9, so is DEF. And because DEF is already a multiple of 5, we know that 45 divides DEF. Thereafter, I did a few more algebraic manipulations of the equations we have, but I couldn't find anything. So once again, I wrote a little computer program, which brute forced the issue at this point. With the restrictions we found so far, it could quickly find the solution. Afterwards, when I started to work on this video, I looked at the grid again, and I realized that the geometry of how the numbers are laid out actually helps. Since E is the middle digit of 2 numbers, which are closely linked through the given clues, we can actually make more inference at this point. Let me quickly show you what I saw way after the 13th of December. Let's put the 45 divides DEF conclusion aside for a while. If 9 divides D plus E plus F, which it must because DEF is a multiple of 9, then D plus E plus F can only be 9 or 18. Theoretically it could be 27 if all 3 of the digits are 9, but we already know that F is 0 or 5. Then clue 4 tells us that BEH must be 9 times 9 or 9 times 18. 9 times 9 is not a 3-digit number, so it's 9 times 18, 162. Next we use the fact that 45 divides DEF again and simply look at all multiples of 45. There's just one 3-digit multiple of 45 with a 6 in the middle, and it's 765. With this, we solved a big portion of the grid, and now it's relatively easy to apply the remaining clues to the missing digits. So yeah, I went to the computer solution again, probably should have stared at the problem a bit longer. In any case, day 14. The function f of x equals ax plus b, where a and b are reals, satisfies this inequality here whenever x is between 0 and 3. What is f of 200? Probably the easiest solution is to plot the functions on the left and on the right in the inequality, and we see right away that they touch at the point 2, 3. So our line must run through this point and have the same slope as the functions at that point. That means we know that f of 2 must be 3, and the slope at 2 must be whatever the slope of, say, the quadratic function is. And then we have two equations for our two parameters, a and b, We can solve it. The line is 2x minus 1, which also fits the graph I painted. And f of 200 is, of course, 399. Technically, one should prove that the blue and violet functions touch at the point 2, 3, but for a puzzle we can skip that, I think. Day 15. Another puzzle where I'm still not satisfied with my solution. What is the smallest 3-digit number whose first digit is 4 and for which the arithmetic mean and the geometric mean of its digits are both non-zero integers? If we look at the average, we sum up all the digits, divide by 3 and want a non-zero integer in return. Similar for when we multiply all digits and take the third root of it. There's an obvious solution, namely if all digits are equal to d, then both the arithmetic and geometric mean will be d. So in this case, we immediately know that 444 is a candidate, but it is not necessarily the smallest one. I have no good idea how to find the smallest solution. Again, very unsurprising, I wrote a computer program that iterated through all 100 numbers and checked the arithmetic mean and the geometric mean. And 444 is the only solution here. I would like to have a general number theoretical statement, however. One thing you could find is, if you look at n digits, and if the geometric mean of them is supposed to be an integer, then the product must be a power of n. That means that all prime factors that appear somewhere in a digit must appear a multiple of n times in total. In particular, we can have no 5s and 7s unless we want the obvious solution where every digit is the same. If you have 1 5, for example, as a prime factor in a digit, then there must be at least n 5s overall. But because 5 can only go once into every digit, it must be equal to every digit, and then we get a number with just 5s. That only leaves 2 and 3 as prime factors for our digits, if we want to have a non-constant solution. But I didn't see how to proceed from here to get a general strategy, a general statement, especially in combination with the arithmetic mean. I think I'll revisit this problem in the future, but for the concrete puzzle here, it's 444. Day 16. What is the smallest 3-digit number that cannot be written as the sum of 2 or more consecutive positive integers? Unfortunately, that is another one which I just knew. All numbers that are not powers of 2 can be written as the sum of consecutive integers. So what we're looking for is the smallest 3-digit power of 2, which is 128. The proof that all numbers except the powers of 2 can be written as such a consecutive sum is not so super short that I would want to reproduce it here. And as I said, I just remembered the fact from my university days. So I will leave a link to a Stack Exchange post where there are 2 nice solutions to these questions, and we will just carry on. Day 17. If you expand a plus b plus c to the power of 2, you get a polynomial that has 6 terms. How many terms does the expansion of a plus b plus c plus d plus e plus f to the power of 5 have? Initially, I didn't see how to count the number of monomials we get, and I simply checked whether Wolfram Alpha would do it for me. It turns out Wolfram Alpha can expand it, and it has precisely 252 terms. I revisited the problem the next day and realized it could be described as pizza. Let me explain. We want to construct monomials of the form a to the I times b to the j times c to the k and so on, such that the exponents sum to 5. This can be reformulated as looking for strings of 5 characters that can be a, b, c, d, e, or f. Now, this is the same as finding all the ways 5 people could order pizza from a menu with 6 options. The order is not relevant, since we're ultimately concerned with which items we end up with, not the sequence they were chosen. No matter which order the delivery person brings the pizzas in, we can always sort them by their toppings ourselves, just like we can sort a string of letters alphabetically. Consequently, we need a combinatorial formula for drawing k items from a set of n elements, with repetition, but ignoring the order. It is n plus k minus 1, choose k, or here 6 plus 5 minus 1, choose 5, which indeed equals 252. If you haven't seen this formula before, I leave a link to the stars and bars Wikipedia page in the description, which is the standard way to prove it. Formulating these kind of situations with pizza instead of just sets of characters is probably not necessary, but it always makes more sense to me this way. Now let's move on to day 18. What is the smallest 3-digit number that can be written as the product of 2 or more consecutive integers? My first idea was to look at the case of 2 factors. If we have two consecutive numbers and multiply them, they should be approximately plus minus 1 the square root of the result. The smallest 3-digit number, 100, is conveniently 10 times 10. So I looked at numbers close to that. 9 times 10 is too small, of course, but 10 times 11 works. Just to be extra sure, I looked at all divisors of the numbers from 100 to 110 to see if I missed any potential consecutive products. But no, 110 is the solution. Day 19 and another grid of numbers. Here we have the division at the end of the columns, so there's no danger of having these weird fractions as from the last iteration of this kind of puzzle. This puzzle here I really enjoyed. It made me feel like I understood what was going on. In the end it's still just tree search or bifurcation or whatever you want to call it, but it was always quite straightforward where to look next, and the number of alternatives always reduced nicely. So let me take you through my solution. I started in column 2 because with the division at the end, we know the first two numbers multiplied together must be a multiple of 35. This is of course only possible if they are 5 and 7, and we divide by 1, because otherwise the product would be far too large. The next thing to realize now is, in the last row, we have the first box minus the last box plus 1 equals 2. We can reformulate that to say the first box must be 1 larger than the last box, which is very restrictive and therefore helpful. Next we look at this third column. The first two numbers multiplied together must be a multiple of 18. So they must be 18, 36, 54 or 72. 90 would be too large. We can't get that with two single-digit numbers. It also can't be 18 though, as the bottom right box can't be 1, since we already used a 1. The box in the bottom right also cannot be 4, because then the bottom left box must be 5. And you already used 5 up in column number 2. That leaves 2 and 3 as possibilities for the bottom right box. If we now look at the bottom left for a moment, we know that it is 1 larger than 2 and 3, so it's 3 or 4. If we shift attention now to the first column for a moment, we know that we need something divided by 3 or 4, which gives us 4. So the first two boxes together are either 12 or 16. The only ways that are still possible are 2 times 6 to give 12, or 2 times 8 to give 16. 3 times 4 to give us 12 is not possible, because then the 3 would be blocked in the bottom left. In any case, we always have a 2 in the first column. That now means that we can't use the 2 in the bottom right box, so it must be a 3 there. From this we get a 4 in the bottom left, and the 2 above it in column 1 gets an 8 as a partner. If we now go back to column 3, we have 3 times 18 equals 54 for the product there, which leaves us with 6 and 9. Now we basically have everything we need. We can stare at the second row now for a bit and see that we need 2 plus 7 minus 9, and the rest of the grid is then a simple matter. Maybe the first two iterations of this grid puzzle also had such nice sequences of conclusions, but then I didn't see them. Here I enjoyed this solution path a lot. Day 20. Here I was unsure because it seems super simple to me, and this is always a bad sign. How many ways can 5 balls labeled 1 to 5 be put into 4 boxes labeled A to D, so that no box is empty? Firstly, in the last column of the example, we see that in the top right in box B, we have the 2 ball below the 1 ball, and in the bottom right, we have the 1 ball below the 2 ball in box A. So the order in which the balls are inside the boxes is irrelevant. It only matters which balls are in which box, and not the order inside the box. The easiest way to think about this problem, at least for me, is the following. We want every box to have a ball. So to start, we look at the situation from the point of view of the boxes. The first box chooses a ball, then the second one, and so on. The first box has 5 balls to choose from, the next one 4, then 3, then 2. Now we have 1 ball left over, and it can go wherever it wants. So we look at it from the perspective of this ball. It chooses one of the 4 boxes, and we get 240 possibilities in total. Number 21. How many 20-digit numbers are there whose digits are all 1, 2 or 3 and whose second digit onwards are all less than or equal to the previous digit? In other words, how many numbers are there, digits 1, 2 and 3, where the digits going from left to right are non-increasing, they stay the same or get smaller? My first idea was to do some sort of recursion again, similar to the Fibonacci examples we already had. So I defined myself C of nd to be the number of falling sequences of length n using d digits. i.e. at the end n is 20 and d is 3. If we have c of 1d, that means we have a one-digit number with d possible digits. So there are d ways to do that. And c of n1, this is an n-digit number with just one digit. There's just one such number. We also have a fairly simple recursion formula again. If the number we're looking at does not start with the highest number, then there are c of nd minus 1 such numbers. And if the number we're looking at does start with the highest number d, we can just cut it off. And we have to find an n minus 1 digit number. So it's c of n minus 1 d. As earlier, these cases are mutually exclusive, such that we can add them up. And from here, I iterated this recursion formula a bit, and I think I found the correct general formula. But before I could double check it, I realized that this puzzle can be solved once more with pizza. So I didn't continue here and started from scratch with the following idea. What we actually want to find is the number of all strings which have 20 characters and where each character can be 1, 2, or 3. It's the same argument as on day 17. This is equivalent to 20 people ordering pizza from a menu with 3 items. Again, the order is implicit. If we order pizza 1 a couple of times, we just sort it at the end of our stack of pizzas. And if we order pizza number 3 several times, we move it to the front of our stack. And then we get this non-increasing number we are looking for. And for the result, we use the same formula as before. Number of items plus number of choices minus 1 choose number of choices. So 22 choose 20 equals 231. While I think the recursion formula I found at the beginning was a good exercise, this is of course much nicer. And it also shows you how you can transform problems into another, which also happened on days 6 and 7 with the Fibonacci sequence. Here it's not really about numbers, but about the sequence of different characters. Alright, let's go to the final stretch of the puzzle calendar. There are 4 ways to pick 3 vertices of a regular quadrilateral so that they form a right-angled triangle. In another regular polygon with n sides, there are 14,622 ways to pick 3 vertices so that they form a right-angled triangle. What is n? Just reading the puzzle, I didn't have any good ideas. So obviously I wrote a computer program to solve it. And it quickly showed me that the answer must be between 100 and 200, and with a bit of bifurcation I landed on 172 as the answer. Since I did this in Cinderella, I tried to visualize a couple of those triangles directly, and as soon as I drew the example with n equals 10 to see what's going on, I thought, oh, it's a circle. Then it's obvious. So that's always what I tell my students. If you have a geometry problem, always make a sketch, even if you want to do something algebraic or algorithmic. Always. Classic case of do as I say and not as I do. If we do make a sketch, we see that the corners of the regular polygon lie on a circle. And one way to state Thales' theorem is the following. If you have 3 points on a circle, they form a right-angled triangle, if and only if one of the edges is a diameter of the circle. This obviously only works if we have an even number of vertices in our polygon. So let n be 2m. If we want to find such a right-angled triangle, we have m diameters to choose from, and we are left with 2m minus 2 places where the third vertex can go. And if you multiply those possibilities, we get an equation for m, which we can solve. To emphasize, always make a sketch if you have a geometry problem, is the lesson here. Day 23. How many ways are there to split a 10 by 10 square into 3 rectangles, whose sides all have integer length? The better way to think about this, as the example above shows, is not integer length, but we want to cut the big square along the grid lines that are drawn at integer coordinates. Let's look at this image here for the 10 by 10 case. My first idea was to make this more general, to look at an n by m rectangle and cut it into, let's say, k pieces, but I didn't really want to do it. It sounded very complicated, and after a day or two I decided, okay, let's stick with a n by n square split into 3 rectangles. My first idea to find some regularity for these subdivisions was the following. We have 4 corners in our square, but 3 rectangles. That means one rectangle must cover 2 corners. And because they are rectangles, it must be 2 neighboring corners, which are occupied by the same rectangle. So for now, assume this quote-unquote big rectangle is on the left-hand side. The other 2 rectangles can be built in one of 2 ways. Firstly, we can have a second vertical line, so all rectangles are like parallel. The first rectangle can be at most n-2 units wide, because we have to have space enough for 2 more rectangles, with width at least 1. And the second rectangle, well, it has a space that's n-k wide, if we call k the width of the first rectangle. But we also need at least 1 unit for the last rectangle. So the second rectangle can be at most n-k minus 1 units wide. This leads to the formula on screen. Because we can also rotate the whole configuration to have horizontal rectangles, we have to multiply this by 2. We can simplify this to n squared minus 3n plus 2. Secondly, we also have this big rectangle on the left-hand side, and then we cut the remaining space into 2 by a horizontal cut. Now a similar argument as before. The first rectangle can now be n minus 1 wide, and the upper rectangle on the right can also be n minus 1 tall, because all we need to build the third rectangle in the end is a 1 by 1 square. And because the width of the first and the height of the second rectangle are independent of each other, we can just multiply them. And now we can rotate this configuration 4 times, such that the big rectangle is either on the left, top, right or bottom. Then we can expand this expression, add everything together and plug in n equals 10 to get our actual answer for this puzzle. Last one. What is the smallest 3-digit number whose binary representation starts and ends with 1 and does not contain 2 zeros in a row? An obvious candidate for such a number would be one where there are only 1s in the binary representation. These are precisely the powers of 2 minus 1. The smallest 3-digit one of those is 127. So we can just check all the numbers from 100 to 127, either manually or by computer, and we see that 107 is the smallest one, which fulfills both conditions. I'm sure there's a number theoretical interpretation for what it means to have a 1 at the end and no double zeros in the middle, but here there are just so few numbers to check that it's easy to just brute force it. And that's it. That's the way how I solved those 24 problems. I was using the computer much more than I probably should have. Thinking a bit more would have been good, but at the end of the day, it was also a nice coding exercise to get those programs running, so I'm happy with that. The last thing to talk about is the overarching super puzzle I mentioned in the beginning. Here are all the clues. Each one is created from the 3-digit number we found during the daily puzzles. I, however, don't think that it would be particularly interesting for you to hear me going through the full solution. You might only appreciate it if you look at these clues a while and maybe try it yourself. All I want to do is show you the main argument you need to solve it, or what I think the main argument is. There are obvious contradictions like clues 3 and 17, so there must be false clues. Moreover, there's one clue, number 23, which says the clues on day 9 and day 23 are false, so it's self-referential. If it's self-referential, there's either a paradox and we can't say anything about it, which is very unlikely in the case of a puzzle competition, or we can actually deduce whether this clue is true or not. And if you do that, you can unravel everything else. And it's mostly bookkeeping after that point. And that concludes everything I have to say about Matthew Scroggs' puzzle calendar. It was very fun, even though I didn't always manage to solve every puzzle on the day it came out. And maybe you found my thought process here and there interesting. If you do want to see me do a live solve of the next puzzle calendar, which would definitely be a much better format than this video here, please let me know in the comments. With that, thank you for watching and until next time.